In this class, we will discuss a design problem on a cold form steel column section. So this is how a problem will be given. We are asked to design a column using a cold form steel section to carry an axial load of 600 kN factored load. Effective length of the column is given as 2.55 meter, that is KL value. Yield stress of that steel is 250 Newton per mm square. Young's modulus 2 into 10 power 5 Newton per mm square. So this is the data. Now, whenever we are going to design any problem, any structural member, either we have to calculate the area required if it is an axial member, or you may have to calculate the section, you may have to assume that section modulus in the case of a bending member. Since column is an axial load carrying member, we will take the whatever area of that particular section required as load into gamma m divided by q into Fy. Actually, this is a thumb rule to initially assume the area required. Here the load given is 600 kN, we will convert that into Newton, so 600 into 10 power 3 into gamma m, as you know it is 1.15 partial safety factor, and Q value is the form factor value which depends on the effective area and the total gross area. It's a ratio of effective area to gross area. Normally you can assume 0.7 to 0.9 in between that, so I will take it as 0.8 here. And Fy is 250 Newton per mm square. If you substitute and simplify, the area required what you are going to get for the given load can be taken as 3450 millimeter square. Of course, it depends on so many parameters. Of course, it depends on the effective length also, all those things. But initially, to have a preliminary design, preliminary section, you can use this thumb rule to calculate the area required. So, depending on this value, whatever required, you can choose a particular cold form steel section from IS 811, just like what you are doing for hot rolled sections using IS 800. Here, IS 811 tables you can choose. In this problem, I am going to choose a double C section or a channel section which is placed back to back like this. So I will choose this section 200 by 80 by 25 by 5 mm. You can observe here this first 200 is nothing but the total depth of that section, or web, total depth of web. 80 mm is the width of flange, 25 mm is the lip width, and 5 mm is the overall thickness. Thickness of all the elements we are taking same. So I have given the sketch of that particular section which is chosen with dimensions. Here I have noted one thing called G. So G is the centroid of this 1C section, which is at a distance of 24.7 mm from this y-axis. Now these are the geometrical properties of this section which is chosen. Now area of this section is 2 times the area of one C section, which is 1830. 3660 millimeter square. So all these geometrical details, properties you can get from this IS 811 table. IXX about the moment of inertia about the horizontal axis. So for one channel section it is 1080 10 power 4 millimeter power 4. For double it is 2 times. And IYY, since the centroid is shifted here, it is not lying on the since if you take one C section or channel section, it is symmetrical about only this x-axis, it is not symmetrical about y-axis. If you take double channel, then it will be symmetrical about both the axes. So see, to calculate this IYO of this double C section, for one channel section we have to compute and we have to multiply it by 2. So for this one channel section, using Parallaxis theorem, so IYY for this channel section is 145 into 10 power 4 plus area of that multiplied by distance between these two. So, and multiply that by 2, you are going to get the IYY for the double C section. Now from that you can observe that here Iyy is less than Ixx. So therefore minimum radius of gyration is nothing but your R minimum is nothing but Ryy here. It is the ratio of square root of Iyy divided by A. So if you substitute and simplify, you are going to get 37.5 mm as the minimum radius of gyration. So normally we are going to calculate that KL divided by R minimum, which is the slenderness ratio that governs the value of the stress and all that are going to develop. So that's why we need the value of R minimum. Now this is one part. So calculation after assuming the section, you have to write down the geometrical properties of those things, including that moment of inertia. Now for the calculation of effective width and all, effective width. So you know how to compute the effective width. I am going to use this IS 801 Indian code. So earlier in the earlier videos I have explained about how to calculate the effective width for different types of elements, for stiffened, unstiffened, for flanges, all those things. Now let us calculate the effective width by taking one C section. So this is one C section I have taken. So 80 mm is the overall width of this flange, 200 mm is the overall width of the backbone, and 25 mm is the overall width of this lip portion, and 5 mm is the thickness. And you know that this internal radius at root is 1.5 times thickness, that is 1.5 into 5, 7.5 mm. If you add the thickness, it becomes 12.5 mm. So the outer radius is 12.5 mm. Now here, to find out the effective width for all these different elements, for the flange, for the web bundle, for the lip, so I am following the codal provisions IS 801 in page 6. So what we have to do is we have to calculate one ratio called W by T limiting. So which is given by 1435 by root 5, root F, where F is in kg per centimeter square. Please note that here F is the basic design stress. It is normally taken as 0.6 times Fy. Here Fy is given as 250 Newton per mm square. So F becomes 0.6 into 250, it is 150 Newton per mm square. This Newton per mm square should be converted to kg force per centimeter square, because we have to substitute here in terms of kg force per centimeter square. If you convert that, you will be getting 1529. So you know how, I think you know how to calculate that. So it is 150 Newton to be converted to kg force divided by 9.81 divided by millimeter square to be converted to centimeter square. That means 10 to the power of minus 2. So this becomes kg force, this becomes centimeter square. If you simplify this, you will get 1529 kg force per centimeter square. This is the conversion. Now if you substitute that value of F in this formula in kg force per centimeter square, W by T limiting value will be 1435 divided by root of 1529, which comes out to be 36.7. This is the comparing factor now. Now let us take one by one. I will take the flange element first. Flange element. So you can see that flange element is stiffened element, because on either side it has got stiffness. So W by T for the flange is, W for the flange is, what we have to do is, from this 80, from that 80 we have to deduct that 12.5 this side and 12.5 this side. So it becomes 80 minus 25. So 55 divided by thickness is 5, it becomes 11. So compare this value with the W by T limiting value. So it is less than 36.7. As per the code, if this W by T is less than W by T limiting, then effective width will be equal to W only. It is 55 mm only. Now coming to the web, it is also taken as a stiffened element, because on either side it has got stiffness. Now in this case, W becomes 200 minus 12.5 this side minus 12.5 this side. So it becomes 175 divided by 5. So this 175 is 200 minus 2 into 12.5. So if you calculate this you are going to get 35. This is also less than 36.7. Then the value of B is taken as equal to W, which is 175 here. Suppose if you get this value greater than this, then there is a formula to find out that V in the same page number 6, which I have used in the last problem, last lecture. Now coming to the third part, that is the lip portion. Lip portion, I will take it as an unstippled element because it is supported on only one side, the other side is free. For the conservative side, I will take this B is equal to W, which where the W is 25 minus 12.5, one side only, so it is 12.5. So now total effective width. So you have for this section now I have to calculate the total effective width. So there are two webs here. There are two webs. So 2 times 175, for one web it is 175, plus there are 4 flanges, 1, 2, 3, 4 flanges. So 4 times 55 for the flange, plus there are 4 lips here, 1, 2, 3, 4. So it becomes 4 into 12.5. If you add all of them, you are going to get the total effective width for the double C section, which is 620 mm. Now effective area becomes this effective width, total effective width multiplied by thickness, because it has got uniform thickness, it is 5 mm. So 620 into 5, so you are going to get 3100 millimeter square. So this is the effective area. So gross area is 3660. Please note here, this is your gross area of the section. Out of the gross area, only this much area is effective. That means most of the load is carried by to this much area. So after that, we have to calculate a parameter called form factor Q, which gives the ratio, which is given by the ratio of effective area to gross area 3100 divided by 3660, so 0.847. So that is the Q value. Initially, you can observe here, initially we have assumed 0.8. So it has come 0.847 here. So after the preliminary design, we are rechecking it. Now, in two ways you can check the strength, compressive strength of that double C section, because it should carry a load of 600 kilonewton over a length of 2.55 meter. Now, there is a thumb rule once again here to compute the compressive strength. So it is reversed. That means here, see in this formula, if you want the load is given by area multiplied by Q into Fy divided by gamma m. That's what I am using here. A into Q into Fy by gamma m. So Q what you have got is 0.847 into area, assumed area is 3660 into Fy is 250 divided by 1.15. You are getting 673.92 kilonewton. So it is greater than 600 kilonewton, whatever is given, therefore it is safe. But actually, we have to compute the value of P using the value of stress value. So now I am referring BS, British code, because it is easy. So in the examination, you will be provided all the codes, BS code also, IS code also. So this part I have done using IS code, and this part I will be using by BS code. So there will not be much difference. So because it is easy, I am following that. Now, according to BS 5950 part 5, if you go to page 30 of the code, in table 10, there is a table given. It gives the values of compressive stress values. Compressive stress values for different values of lambda, there is tenderness ratio KL by R minimum and this Q into root of YS by 280. If you refer the code, so I will calculate this value Q into root of Ys by 280. Here please note that Ys is the given yield strength, which is 250. So 250 by 280 under root into Q value what we got for this section is 0.847. If you simplify this, you get 0.8. This parameter you are getting 0.8. And KL by R minimum. So KL is the effective length here, 2.55 meter, that is 2550 mm, divided by R minimum we got here 37.5. Substitute that, you will get 68. Now taking these two values, using the table 10 in page 30 or 31, there are tables in 3-4 pages. So just you have to take the value of this compressive strength directly if you are not getting the exact for the exact values, you have to interpolate. Here of course you are getting for 0.8 of this value, and for 68 you have to interpolate, because the values are given for between 60 and 70. You have to interpolate to the corresponding compressive strength of interpolation. You are getting 191 Newton per mm square. So when this is multiplied by the compressive strength, means it is stress. Actually this is stress only. When this is multiplied by the area, gross area of that particular double channel section, so that is 191 multiplied by 3660, you are getting 699.06 kilonewton. You are going to get in Newton converted to kilonewton. So you can observe that is greater than whatever load they have given. So strength is greater than the load. So therefore it is safe. So you have to follow this method, because this is the exact method of after getting the stress value, after reading the stress value from the table, you can multiply that stress value by the area of that section. So to get the load carrying capacity of that particular section over that length. So over that length. Here length is given as 2.55 meters. Suppose if the length is more, then this Km will be more and this value will be more. This value will be more. When this value is more, this will be lesser. Please note that as the tenderness ratio increases, the strength value reduces. So when this is reduced, then automatically this value also will be reduced. So you can always decide. So for up to what length you can provide to have that particular load. So therefore, a design problem, it depends on so many parameters: the load value, the effective length value, yield stress value. So for all those things will govern the selection of a particular suitable section for a column. So in this problem, I have considered a double C section, a channel section, because the load is more here. Suppose if they give a load around 250 kilonewton or 300 kilonewton compressive load, then you can go for a single C section, or sometimes you can choose a hat section also. So these are the different types of sections you can choose for designing compression member. Hat section you can choose, or else you can go for Z section, something like this, with lips like this. So these are the different types of sections. You can normally this Z section is used for bending elements, whereas for compressive element you can choose either this, or you can choose this, or you can choose double C section like this. So this is how the design steps will run for the design of a compression member using cold form steel sections.